Man managed to conquer the skies just over a century ago, turning a fragile frame of wood and cloth into the most complex machinery on Earth. Today, hundreds of thousands of aircraft fill the skies daily, ranging from massive double-decker metal tubes cruising across continents to invisible supersonic jets designed for elite warfare. But if you strip away the branding and logos, how exactly are they classified? Today, we open a complete engineering and operational investigation into the sky. From general aviation to commercial giants and straight through elite military classifications, this is every type of airplane explained. Welcome to Machinery Explained, before we decode the engineering of flight. A huge shout out to our community here at Machinery Explained. If you love pulling back the curtain on complex industrial engineering, massive heavy equipment, and the precise mechanics that keep the modern world moving, you are in the right place. To our thousands of regular subscribers who join us in the workshop every week, welcome back. If you haven't subscribed yet, hit that button right now and turn on notifications. We break down the world's most intricate mechanical systems, and you don't want to miss our upcoming deep dives. Let's get right into the blueprints. Part 1. The General Aviation Foundation. To understand how the aviation ecosystem is built, we have to start where every pilot begins: general aviation. This category encompasses all civil aviation flights except scheduled commercial airlines. Within this space, aircraft are classified by their propulsion systems, weight, and operational environment. Single-engine piston aircraft. This is the bedrock of flight training and private transport. These planes utilize a single internal combustion engine, mechanically identical to a car engine, to spin a fixed or constant speed propeller. Think of the iconic Cessna 172 Skyhawk or the Piper PA-28 Cherokee. They are lightweight, highly reliable, and optimized for low-altitude, short-distance regional flights. Multi-engine piston aircraft. When an aircraft requires more speed, payload capacity, and redundant safety over open water or mountains, engineers add a second piston engine. Aircraft like the Beechcraft Baron or the Diamond DA-42 allow pilots to maintain flight even if one engine suffers a catastrophic mechanical failure. Turboprops. When piston engines reach their physical performance limits, aviation shifts to turbine power. A turboprop uses a jet turbine core to drive a gearbox that spins a massive propeller. This hybrid engineering combines the raw efficiency of a jet engine with the high low-speed thrust of a traditional propeller. Workhorses like the Cessna Caravan, the Pilatus PC-12, and the twin-engine ATR-72 dominate this space. They are the ultimate machinery for short, rugged runways and regional commuter hops. Part 2. The business and private jet tiers. As we scale up into pure jet propulsion, the machinery transitions into the elite world of private corporate transport. Business jets are built on a strict hierarchy based on range, cabin volume, and engine performance. Very light jets. These are essentially the entry-level sports cars of the jet world. Weighing under 10,000 pounds, aircraft like the Cirrus Vision Jet or the Embraer Phenom 100 are designed to be flown by a single pilot, carrying 4 to 5 passengers on rapid regional trips under 1,200 nautical miles. Light and mid-sized jets. Moving up the scale, we find the core workhorses of corporate fleets. Light jets like the Cessna Citation CJ4 offer expanded seating, while mid-size options like the Learjet 60 or Bombardier Challenger 350 introduce full stand-up cabins, high-altitude performance to fly above severe weather and cross-continental range. Heavy and ultra-long-range jets. This is the pinnacle of civil engineering before reaching commercial airline scales. The Gulfstream G700 and the Bombardier Global 7500 use incredibly powerful, ultra-efficient turbofan engines. These machines can cruise at Mach 0.90 at 51,000 feet, bridging cities like New York and Tokyo non-stop in complete luxury. Part 3. Commercial airliners. Moving the masses. When it comes to mass public transit, Commercial airliners are divided into three distinct operational and structural categories. Regional jets connect smaller local airports to major international hubs, typically seating between 50 and 100 passengers. Models like the Embraer E195 or Bombardier KRJ 900 utilize downscaled turbofan engines optimized for quick cycles, frequent takeoffs, and landing on shorter runways. Narrow-body aircraft, also known as single-aisle airliners. These form the absolute backbone of global domestic air travel, driven by high-bypass turbofan engines. The Boeing 737 and the Airbus A320 families carry between 150 and 240 passengers. Their engineering focus is pure economic optimization, maximizing fuel efficiency per passenger mile on short to medium-haul routes. Wide-body aircraft, the heavy giants of intercontinental travel. Featuring a twin-aisle configuration, these massive structures are engineered to handle the staggering stress of ultra-long flights. The twin-engine Boeing 777 and Airbus A350 use the largest turbofan engines ever built to haul up to 400 passengers across oceans. Meanwhile, four-engine double-decker anomalies like the Airbus A380 represent the absolute limits of traditional aerodynamic scaling. Part 4. Special mission and specialized aircraft. Not every airplane is built to carry people or standard cargo. Some of the most fascinating engineering in aviation belongs to special mission aircraft, built for highly specific physical environments. Cargo and heavy lifters, while standard cargo planes are converted airliners. Purpose-built military and industrial logistics giants are engineered from scratch. Look at the C-17 Globemaster or the Lockheed C-5 Galaxy. They feature high-mounted wings so their giant engines don't ingest debris on unpaved runways, rugged multi-wheel landing gear to distribute weight, and massive nose or tail ramps for heavy armor and machinery. Amphibious aircraft and seaplanes engineered with specialized hull shapes or massive floats. Planes like the Canadair CL-415 can land directly on water. The CL-415 is a legendary firefighting super scooper, designed to skim a lake surface, ingest over 1,600 gallons of water into its internal tanks in just 12 seconds, and immediately take off to fight wildfires. Part 5. The ultimate military classifications. Finally, we cross into the bleeding edge of aerospace engineering, military warplanes. The United States and global militaries categorize these platforms with a strict tri-service designation system that instantly defines an aircraft's mechanical purpose. Fighter aircraft are engineered exclusively for air-to-air dogfighting and establishing air superiority. These machines, like the F-22 Raptor, prioritize thrust-to-weight ratios greater than 1:1, extreme maneuverability via thrust vectoring nozzles, and advanced stealth radar cross-section reduction. Attack aircraft are built for low-altitude close air support to hunt enemy ground forces. The iconic A-10 Thunderbolt II is essentially a flying titanium bathtub wrapped around a 30-mm rotary cannon, built to survive intense ground fire. Bomber platforms are massive, heavy strategic platforms designed to carry payload deep behind enemy lines. This ranges from the high-altitude, long-range B-52 Stratofortress to the flying wing stealth design of the B-2 Spirit. Special electronic aircraft are modified with massive radar radomes or electronic jamming suites. The E-3 Sentry AWACS acts as a flying command center, coordinating entire air theaters from the sky. Tanker aircraft function as flying gas stations like the KC-46 Pegasus. These are heavily modified airliners engineered to transfer thousands of gallons of fuel mid-air to thirsty fighters and bombers, extending global military reach indefinitely. Conclusion: every single aircraft in the sky is a masterclass in compromise. To get more range, you need more fuel, which requires bigger wings, which creates more drag, requiring more massive engines. The entire history of aviation is simply the story of engineers balancing this delicate physical equation to push humanity further and faster through the air. Which category of aviation engineering fascinates you the most? Are you a fan of the sheer mechanical scale of wide-body airliners, or does the raw, high-G performance of military stealth fighters catch your eye? Let's spark up a discussion down in the comments. If you enjoyed this comprehensive breakdown of flight machinery, make sure to smash that like button to help push this into the YouTube algorithm. Share it with a fellow tech or aviation enthusiast, and subscribe to Machinery Explained so you never miss an episode when we pull apart the world's most incredible physical systems. Thanks for hanging out in the workshop with us. Stay curious, and we will see you in the next breakdown.